So the takeaway here needs to be that the most important aspect of a line is the slope and a point on it, whether it's the y-intercept, in which we have the slope-intercept form, or if it's just an arbitrary point that's on the line. We still need the slope and the point on it. Even the linear equation, as I've shown, the slope is hiding here. And again, this idea of slope is at the heart of everything we're going to talk about. So let's focus on making lines. So let's compute the slope of a line between 2 points. So let's say between the points, we'll call, I don't know, 1, 3, and the point Q, 2, 1. So we can draw the graph of what this looks like. So I've got a XY axis, and I'm looking at the point 1, 3 is maybe about here, and the point 2, 1 is somewhere around here. And so the line through those 2 points, let's see how well I can draw, would look to connecting these 2 points. We get the line. So what's the slope of this line? What is the change in y over change in x? So we know that slope is the change in y over the change in x. This is your first time seeing this symbol. This is the delta Greek letter that corresponds to our D, and should remind you, the reason why I use this delta is it should remind you that we're talking about the difference. Whenever I talk about change, I'm talking about a difference, so subtraction. So change in y simply says, okay, let's look at the difference of my 2 y points. So my first y point is 3, the second one is 1. So the change in y is 3 minus 1. Whereas the change in x, again, I'm going to use it the same order. I can't switch orders. So I use 3 here and 1 there. So now I'm going to use 1 for my x value and 2 for my second x value. So it is 1 minus 2. So this is equal to, so 3 minus 1 is 2. 1 minus negative 2 is negative 1. And so the slope is negative 2. So now I know my slope. And a perfectly good equation then of this line would be y minus 3 is equal to negative 2 times x minus 1. So notice I use the point from P to fill in my y1 and x1 from my point slope form, and here's my slope. The same equation, so this line, this isn't the unique equation for the line, because I could have used the point 2, 1. So an alternative form of this equation is y minus 1 is equal to minus 2 times x minus 2. Both are perfectly good, valid equations of this line. The only time you end up with a unique form is when you put it into slope-intercept form. So you should pause this video, take a minute, put this into slope-intercept form. So you're going to have to multiply through by negative 2 and bring the 3 over. Do the same here, and you'll see they both give rise to the same intercept. In particular, it's when x is 0, y is going to be 3 plus 2, so it'll be 5. So an application in lines, a very simple application, with regards to something moving in a straight line, moving up and down. So we may know its velocity, which is how far it changes over time, and we may know its position at some given time. So for instance, let's say that we have some particle, and when time is 0, its position is 3. And then we let some time go by, and so maybe 2 seconds later, time equals 2, and the new y position is 1. So this particle is moving in a straight line, and we'd like to know its position. So this right here gives us the rate of change, will give us the slope, because when time is 0, we know its y position. When time is 2, we know its y position. So again, we can map that on a graph. So here's, instead of this being the x-axis, this is the t-axis, and this is the y-axis. So when t is 0, y is 3. So we're right here. And then when t is 2, y is 1. And so we're right here. So kind of similar to the previous problem, we know that our line or our particle is moving, and its path will look like, or the graph of its movement will look something like this. So when t is 0, y is 3. When t is 2, y is 1. I know it's not going through the point. So what's the equation of the line? Well, just like before, we need to know the slope. So our slope, in this case, is the change in y. And now it's the change in time. But nothing, just because I changed to a different variable doesn't change the slope idea. So it's still 3 minus 1. So that's our position when time is 0 and our position when time is 1, divided by 0 minus 2, which is 2 over minus 2 or minus 1. And so our equation would be y, and it doesn't matter which point we use. Let's just go ahead and use the first one. So y minus 3 is equal to negative 1 times x minus 0. And we can leave it that way, but having a 0 is an empty placeholder, so I might as well move this around and put it in the slope-intercept form. So if I distribute the negative 1 to the x and bring that over, it'd say that y is equal to negative x plus 3. And now we know, and I apologize, I switched from t to x's. So if you will, if you're taking notes, we should be erasing these guys and calling them t instead of x. I apologize for that, switched in the middle of the game, but t and t. So now we know the position of our particle at any given time. It's a linear relationship. And so as we knew, the particle starts at 3, and then it's going to decrease 1 unit for every unit in time. So you can see a particle moving in a straight line. We can model its position.